Okay. Hello, everyone. Thank you very much for coming to this talk. The idea for this talk came from a general theme that seems to be emerging throughout engineering in general. Maybe software engineering is particularly acute in that the amount of knowledge that is required for an engineer to do his job these days is just growing exponentially. We've started talking about full stack development now, and that requires such a breadth of information and such a depth of information that it's actually becoming a bit hard to manage. And taking that question forward, engineers, I think, are actually starting to become less engineers. So traditional engineering is taking a problem and solving the problem with known, tools or policies. I think engineering is actually becoming more of a research task. But I don't think that most engineers see themselves as researchers. They still see themselves as engineers. So this talk is going to be a little bit about that. So my name's Phil Winder. I've got a small company in the UK, winderresearch.com. Check it out. It's split into three parts, really. The first part is trying to prove to you that, in fact, you're not engineers anymore. You really are researchers. I'm then going to take a look at some great researchers, at one in particular, and I think that might help to bring traditional ideas of researchers back to earth. And then finally, I'm going to talk a little bit about how you can actually use some research methodologies in your job to do more research, if that's what you so wish. So first, we need to define what research is, and the traditional ideas of research involve a scientific notion of doing some research. And usually, scientific research is based upon trying to expand knowledge, trying to catalog and quantify knowledge as a thing, just for the sake of gaining more knowledge. I think it's a little bit different in industrial research, in engineering, mainly because we usually have a goal, and we live in the vast majority of projects that we're talking about, the goal is capitalistic in nature. We are trying to make money. So I like to sort of reframe research more of with the definition of an attempt to improve or advance something. And that thing could be a product, an idea, it could be a process, like a manual process, it could be anything. But it's suitably vague to both contain scientific definitions and industrial definitions as well. And the first thing we need to learn is, like, why would you do research in the first place? Why is research even a thing? And for science, research is the thing because there's a natural human tendency to want to try and understand and describe the world that we live in. So we'll look a little bit about what academic researchers do in a minute, but industrial research is generally done for a reason, and that reason is money. So if you ever go to your boss and you need to say, well, just on a general scale, why should we do research? And the reason why you should do research is because it makes money. This is an average over a significant number of industries. We've got industries ranging from tech all the way down to manufacturing, and on average, all of those industries produce a return on investment between 10 and 30%. And it's quite a vague result, in fact, because it's so spread over so many industries. The statistics of that number are really, really broad. There's really long tails on that. So you've got anything from 0% all the way up to the Googles and the Amazons and such. But I think there's like a secondary reason why people would want to do research in a company. And I think that the reason is that it breeds, I think innovation in a company makes that company more exciting to work at. If you're in a stale, big, large enterprise, you're very siloed into a single job, personally I find that quite boring, and I think that could be true for most people. I think if you allow and you trust for engineers to innovate, then that breeds enthusiasm, not just within those people, but without the entire business as well. So I think there's definitely implications for something more than just making money. So when we think about a researcher, what is a researcher? Your ideas of by the way, this is the first of many fantastic drawings that you're going to enjoy throughout the presentation. I hope you like them. When you think of a researcher, you usually think of someone who works in a university, maybe a scientist. So that type of person, the qualities of that person, you think of them, a scientist, being this grand genius who sits under trees and apples falls on their heads, and they'd come up with these general theories about life itself. That's not true. That is not what research is. And the problem with that idea is it breeds these misconceptions about research. And it's basically around this idea of not being smart enough. Like, I don't have a PhD, I'm not smart enough. Only academics have real time to do research, and that is absolute nonsense. This is some research done by Cambridge University. You probably can't quite make out the text, unfortunately, but I'll talk you through it. The idea of this research is to try and document what an academic researcher does on a day-to-day basis. I've got two slides. This first slide is for an early career researcher. So this is for a guy that's just finished his PhD, just started his postdoc, maybe responsible for a couple of PhD students and a little bit of lecturing. We've got different color codes in here. We've got blue for research, red for training, green for admin, and gray for miscellaneous. And we'll just go through his day. His day is training from London, marking, supervision, journal club, and then he's reading out and printing through and going through grant proposals. He does more lectures, he has the Skype interview, has some lunch, some admin, more proposals, a bit more supervision, and then more proposals. So during that entire day, for this one day, for this early career group researcher, he has done exactly zero research. All of the research that he has done has gone into that grant proposal. He has done technical pre-sales. This is a senior researcher. So this guy is probably responsible for 5 to 10 people, maybe postdocs, maybe PhDs, does primarily lecturing. And let's have a look at his day. So he starts off learning Chinese. Tough way to start your day. He's dealing with emails and then, again, editing a proposal for a volume that he's a director of. He has a big drop in satisfaction there. So the y-axis is satisfaction and is unsatisfied because he's responding to an issue about his course. And then there's a few more things, supervision, a bit more preparation, and then finally he goes home for dinner. And the key difference between him and the early group researcher is basically what time he goes to bed. If you see at the end there, there's 3 dots starting at 8 p.m. going all the way up to midnight. And in those 3 dots, he's writing an article. The only time throughout the day that he has had time to do any real work, anything productive, is on a night time when he doesn't have any other things to do. So, last little bit of academic research, really. This is a job posting that went up a couple of weeks ago for a university in the UK. And I've highlighted some parts of that job spec that are required. Communication skills, interdisciplinary, policy relevant. The focus of the research must be, so this is the university telling this prospective lecturer and researcher that you have to do research in this particular subject. You must have a publishing track record, lecturing experience, attracting research funding, knowledge and exchange. These guys, they do have specialist knowledge and they have spent a long time learning their art, but the vast majority of their job is some form of teaching or mentoring, lots of admin, lots of sales, an amazing amount of sales in academia, and finally just a little tiny bit of research. I think that this applies actually to software engineers if you start thinking about what you do on a normal day. You too have specialist knowledge. You've spent years learning your craft. You too are probably involved in some sort of mentoring scheme. And you too have probably too many meetings that meetings that you don't like. And whether you like it or not, being part of a business, you also need to be part of this sales process, and probably to a lesser extent than an academic. And finally, you do some delivery. So the jobs that an academic does and what you do are actually very similar. So going back to this question of what is research, generally you could say that it's the pursuit of knowledge, to develop a new understanding and then deliver or enact upon that knowledge to make something better. And on a day-to-day basis in your software engineering life, you probably go to Stack Overflow quite a lot. And in your pursuit of knowledge, you are asking questions like, why the fuckity fuck is HTML have a color code called Chuck Norris? Like, seriously? And then you find this out and you develop a new understanding. You sit there with your head in your hands and going, software engineers, they think they're funny. They're not funny. I don't think I know of one software engineer that has become a comedian. So please, don't be funny. And then we finally realized that Chuck Norris really is a color and we really can use it. We need to enact our new knowledge. And we do that with our old friend, copy and paste. So in a nutshell, that 1 minute thing that you're doing every single day, day in, day out, that is a mini iteration of research. So if we accept that we are actually researchers, not just engineers, can we do it better? So I'm going to talk now about this guy called Francis Crick, who is a British biophysicist. He's most known for his work on DNA, and he discovered DNA in about 1953, and he got the Nobel Prize for it in 1962. He did this work with a guy called James Watson and Maurice Wilkins. So James Watson is actually from Chicago and was educated in Chicago, so big up Chicago. And the reason why I want to talk about him is because it's a fascinating story. He's thought of as one of the most important, most influential scientists, not just of like the last century, but of all time. He's really up there with the greats. But what I find so interesting is that his story is kind of so average, it's so normal, and it's great to bring these people back down to our level and understand where they are. So his story starts something like this. He was born in 1916, and he went to school. He was lucky enough to be a little bit wealthy, so he was able to go to school, and private school, which wasn't common in those days. And by the time he left school, he was expected to go into university, but he couldn't get into university. No university would have him. It took him until he was 22 until he managed to get, bearing in mind that in those days you left school when you were 14, it took him until he was 22 to get into university. He finally went to university in London, a university called UCL, and he did an undergraduate in physics. He was okay. He was an average student. I think he got a second-class degree, nothing spectacular, but he managed to persuade someone to start on a PhD. And this was actually the beginning of a real struggle for him because he really didn't enjoy his PhD. He didn't enjoy the subject. He thought it was very boring. And then World War II broke out. He did a lot of work during World War II and gained a bit of a reputation for being a hard worker, basically. And finally, at the age of 32, he actually finished his PhD. So by the time he was 32, he hadn't done anything, basically. He was not known as a scientist. Nobody knew him. People thought he was quite annoying, actually. They didn't like him at all. But then, over the next preceding decades, he kind of refined his way of working and learned how to work to his strengths and to his benefits. And he, quite rightly changed the world. These are some quotes from his biography. He used to go home to his wife, very often, saying, "I found this new amazing thing." Like I'm sure you people go to your spouses and they go home and, "This new framework, this new JavaScript framework, it's amazing. Let's talk about it over lunch." And she said you were always saying things like that, So he obviously had far more ideas than he could ever handle. So much so that James Watson actually soon began to worry about this idea of DNA. He didn't trust that it was actually going to follow through because they only had these ideas in their head. They couldn't find any experimental proof that it existed. They thought it was all a pipe dream. But they took a step back and looked at all the current research and found that they'd actually made a lot of mistakes along the way. They needed to iterate on this loop again. They needed to repeat their research and find their hypotheses. And a key thing that he said that he enjoyed the downs, the bad parts, as well as the ups, because it helped him in the future to actually present this as a story. The ability to present your work as a story really helps in the dissemination of your new information, whatever it may be. John Milton said the important thing is to be there when the picture is painted. And I think that's true in software engineering, not just in life in general, but it takes a long time to learn from your mistakes. He said it was partly a matter of luck, partly good judgment, inspiration, and persistent application. And that was the key thing about Francis Crick. There were two main parts. I missed it. There were two main things to his character. He was a big communicator. He would talk to everybody and everything, and a lot of people couldn't work with him because he spoke too much. But he bounced ideas off other people, and he needed other people in order to do his work. Without these other people, without these James Watsons and other people throughout his life, he wouldn't have been able to do his work. But the key part was persistence. He was insanely productive. He could concentrate for 8 hours at a time. His willpower was so strong that he could do pretty much anything he put his mind to. So Francis Crick was confident but humble at the same time. He was critical but collaborative. He was ambitious yet realistic. It was thorough, but he also knew when to stop. So if you take wrong slide. If you take all of the ideas that all of the qualities that he had and munge them into a software engineering perspective, then when we're doing research, there's actually there's a huge list of qualities and traits that we need to improve as engineers to be better researchers. I've generated a little picture here, and I don't expect you to read through all of them, but generally they fall into 4 camps. There's technology, business, internal, and external qualities. Technology is self-explanatory. I'm not going to go into that. But it's key to always remember the business in this, because the research that you're doing it for a purpose, and that purpose is usually for a business. If you have an understanding of the business, then that makes your qualifications for doing research much stronger. But there's also internal and external qualities that you need to work on to be a better researcher. And the main one is perseverance. It is really, really, really hard to do some research thoroughly and well without being persistent. Obviously, you have to be creative and work with others really well. And then external qualities. I've seen many really great engineers that are fantastic at doing their job, but they never externalize the work that they're doing. They never tell anyone about it. They never share their knowledge. And I think that's a key skill in becoming a better engineer, because if you try and tell somebody else about what you're doing, I think it makes it more concrete in your head. I think everyone's experienced that. So the idea of this list, we've got the slides afterwards, and I might write a blog post about it, but the idea is that if you can take a good look at that and score yourself on all of these parts, then you might find some areas that you'd like to improve yourself on, and that will make you a better researcher, and that will make you a better engineer. Okay, so let's move into some more practical steps now. And I call them research patterns. And this is a work in progress. When I do my sort of day-to-day engineering job, I see it as more of a process more than anything. And the way that I'm doing this development is very heavily influenced by research. So I'm thinking about this idea of research-driven development. And it's the process of taking the scientific discipline of research and applying it to the jobs we do on a day-to-day basis. First, we need to understand the science a little bit more. Unfortunately, I think Brian Cantrell, who did the keynote this morning, I bet he stole my slides. So there's a bit of duplication here regarding hypotheses and bugs and stuff. But I'll beat him up at the end of the day because, plagiarism and all that. So a hypothesis is a proposed explanation, usually based on prior experience and background knowledge. A hypothesis is something that you generate every day, every minute in your working life. You are expecting something to happen. And when you do something and that doesn't happen, it's surprising. And that's actually how most science works. They're generally observing something else, totally unrelated, and something unexpected happens. And you use a hypothesis in order to define what you're about to do. The rest of the work is basically generating results to support or do not support that hypothesis. The scientific method is a formalized iterative loop of taking a hypothesis and then performing observations or measurements and creating a formulation and testing of those ideas and then modifying the hypothesis again at the end. From Wikipedia, they show this chart. It's a little bit verbose, but it's okay. It basically starts off at the top with making observations. Once we've got an observation, then we think of interesting questions and formulate hypotheses. We develop testable predictions to test those hypotheses. We gather data, we run our software to test the predictions, and then we develop new theories and keep repeating like that. And just to make that a little bit more concrete, I think it's worth looking at our bug problem again. So this is slide 38, at slide 38, and you could tell he's an engineer because number one, he's got an at the front of his name, and number two, he's got hair in the wrong place. He's got hair here instead of hair here. Hair should be here, not here. And he has a bug. This is his bug. He's got this little tiny bit of code, and when he runs it, it produces this output. We've got a simple flag at the top that's saying if the flag is true, then do some work. But we've set the flag to false, and it's still doing some work. And as every engineer knows, it's probably his most famous phrase, and so much so that there's probably a lot of these in your Slack. In fact, you should try and find some metrics how many times the word "what the fuck" has been used in Slack. Because he's like, "What the fuck? What the hell's going on?" So he starts on this formal scientific method loop. He's thinking, well, what interesting questions? I have an observation now. The observation is my code doesn't work, and I need to figure out some hypothesis, some interesting questions to ask about that. Now, when you write at the start, it's actually a little bit hard to formulate that hypothesis, so you have to do a little bit of debugging, and that generally means that you have like a vague hypothesis. You know, the vague hypothesis in this sense is that that bit in the middle doesn't really work too well. So I'm going to insert a little print line just to help me out in the debugging. So I insert the print line, I rerun the code, and now we get blank. I'm like, what the hell's going on? So I've just added a print line, it's not printed, the flag now seems to be working. And then it's like, all right, standing out is ignored. Jesus. So previously, the flag was ignored. Now, the print line is ignored. It's because of that damn slash on the end. It's got that backslash. It's multi-line. It's commenting out that next line. So this new hypothesis is that if I take that slash out, I generate another testable prediction, I repeat my tests, and then we can generate a general theory. And the general theory in this case is I'm an idiot because I made a typo on my code. But you can see that he's very happy about this, and he's doing in fact, I bet software engineers actually have quite strong biceps on the right because they're doing this so often. And like even in such a menial task as bug fixing, it's actually like weirdly rewarding. You know, this process of fixing a problem, finding the problem, and understanding the problem fully. It's a real moment. And that's why engineering is quite enjoyable in general. There's lots of those moments. So this was this type of process has got a formal name in the literature. It's called experimental research, and it's performing controlled experiments to verify hypotheses. It has a comparison between competing designs, and it requires a robust metric. So our metric in that case was, does it work or does it not work? And depending on the nature of the problem, you may need lots of data. So we've all had like flaky tests that are failing in like your CI system where they only fail once every 100 times or something. You need a lot of repeats, a lot of data in order to test your hypothesis. And when we're doing the research, we need to develop this idea of critical thinking as well. We need to ask the questions, why am I doing this? What is it for? Who am I doing it for? It's all the words that you learn about in school when they give you the assignment of writing a story. What, where, when, why. And that critical thinking is an important aspect here because that's what generates the new hypotheses. And the why is super important, especially in business, because you need to be able to justify this to other people, to your boss, to your spouse. Why on earth are you doing this? Josh Greenman put up this, so we're in the US, I thought I'd bring some US-related stuff in it. And he did a little test where he would type, why is insert state so, and then he would get the first hit from the Google result, the first autocorrect from the Google result, and plotted it on the map. And you can see, where are we now? So why is Illinois so corrupt? Come on, guys, seriously. Why is Wisconsin so liberal? Yeah, bloody liberal ragtags. We've got some rather funny ones in there. Why is New Hampshire so white? Good question. Good question. Yeah, that's a good plot. Good set of research there. Very fun. But yeah, more generally, in industry and in business generally, you need to be able to justify your research to your boss. And because we live in a capitalist society, it always comes down to money. Can you, or does your research make money, reduce costs, or save time? If you can frame your research in such a way, then it's far more likely to get accepted by everybody. That's not always true. You can have not, there are other reasons why you might want to do research. But if you can phrase it in such a way, you're far more likely to get it accepted. When we're talking about software research and development specifically, it doesn't necessarily pertain to software itself. So there's another branch, it's like experimental research, it's called action research. And action research focuses more on a particular problem, but it's not necessarily a technical one. It could be a process, it could be a people problem. And this starts to formulate the research process into something we're a bit more familiar with. So there's a purpose, the focus of the relationship, focus of the research, the relations between the things that you're trying to research, the method and the validation. I think that we can generalize that a little bit more. And this is basically the OODA loop, the observe, orient, decide, act loop. And when we're doing research on a day-to-day basis, or whether we're doing a multi-year research project, it always forms a loop like this. We find a problem, we understand a problem, we solve the problem, and then we review what we've done. And each part of that loop is super important. And even more important is the fact that it's iterative. It keeps going round and round and round. You might find that, after you've found that Chuck Norris is a color, that might have knock-on effects for the rest of your subsystem. Maybe you can replace all of your colors with like crazy action names instead of using normal HTML codes. So let's take a look at the bug example again and try and fit that into that framework. Normally, when somebody finds a bug, it's usually a customer or a user, maybe it's yourself when you've been doing some of the code. We need to understand that bug. So in this case, this is a banking bug, so we definitely want to squash this because we don't like bankers. It's got a bowler hat and a tie, you can see, that's why it's a banker. And that's understanding the problem, and then we solve the problem, usually with a hammer, brute force, just whack it until it works. And then crucial bit is the review at the end. We need to review the problem because it might exist elsewhere. There might be other bugs. There might be similar bugs in similar systems, or during the process of fixing the bug, you might have found another bug. But to bring it back to reality a little bit, I think that one of the coolest things about software engineering in general is the scope for research, the amount of scope that doing this job allows for research is remarkable. And you can think of probably something that you're interested in. I think this is maybe quite a typical use case for something like this, is I'm interested in learning a new JavaScript framework or front-end language or something like that. If you like to do that work, that's great, and it's very fun, and I enjoy doing it myself. But you need to spin what you're doing in such a way that it makes sense for the business. Otherwise, you're not going to be able to do it. So rather than saying, I want to investigate Elm, maybe phrase it in a different way. I want to improve front-end developer productivity. And that suddenly spins the question in a way that the business can understand, and it's far more likely to be accepted. The key questions, though, is why? Why would you do this? How long would it take? How much is it going to cost? And you need to really start to pin down some of the specifics about the question that you're setting there. So we've said reduce the lead time on new features. But, I mean, what is the definition of productive? Like, how are we going to measure productivity? Is it as simple as, like, the number of new features over time? Or is it something more complex, like the amount of time people have spent on a particular problem? Baselines are really important. So one of the critical tenets of doing an experiment is this idea of being able to having something to compare it with. So this idea of a controlled experiment where you have a control that continues in your normal process, and then your new work that you can compare against. And if you can say at the end that your methodology or your language or whatever it is that you found during your research is X times more performant, that's good. If you can't do that, then you're not going to be allowed to do research ever again. And then actually the solving the problem is kind of, it's not the simplest. It's certainly probably the most fun part of the process. But it's a bit easier to do because if you've asked the right questions to begin with, you generally know exactly what you need to do. So solving it is actually probably one of the simplest steps, to be honest. But then once you've solved the problem, you need to review. And the review in this case is telling people about your results. You need to tell your bosses and your managers how to save money. You need to tell the front-end engineers that React is shit and Elm is good. And based upon those actions, if you get punched in the face, or if somebody says, you haven't tried X, Y, Z, you might need to repeat this process again. So the final thing I want to talk about is something that is forming in my head. It's not concrete at the moment, but I'll talk about it anyway. Even in this conference and previous conferences and books everywhere, there's been this idea of failing fast. It's this idea of being lean. And when you come across a failure, make sure that you fail early so that it doesn't cost that much. And I have a real problem with that, especially in engineering. Maybe that works in business, but I'm not convinced that it works in engineering. And the reason is that software engineering is very seductive. There's almost like a siren quality to it. Like, you know when you get given a new task or something, the first thing that you want to do is sit down on a computer and start bashing away at the keyboard. Just start writing code. It's so alluring. You don't sit back and think about it. And I think this applies to development and research as well. It's very easy to stop at the wrong point. So rather than fail fast, I would prefer to stop smart. You know, don't just fail immediately because you feel like you're failing or somebody says you're failing, because that might not be the best choice. There's this idea that I have of like of product perfection or perfection, some measure of perfection within your business. It could be it's basically a rate, but it could be like revenue per year or number of features per week or something like that. And there's some optimum where we could be working at, but I don't think we hardly ever get there, because if you fail fast, if you fail too fast, you could be quitting too early. But you know, the flip side is if you keep hanging on and you keep hanging on, you could fail too late. So, you know, what is the goal of this? Well, the goal is, like, throughout your career is to basically do the best job you can. And I feel like that if you do that, then it's satisfying for you, but it's also rewarding for the business as well. And if we can get to this state where we're stopping at the right time, so we're not continuing on products that are, you know, there's no point developing more features, but also we're not stopping too early and missing out on any potential gains. And you'll see that different projects over time have a different potential as well. So this point at where to stop, it's actually really, really hard to define. But one of the things I'm most worried about, and the reason why I didn't like this fail fast idea, was because I think engineers get bored very quickly. They get bored very, very quickly. And as soon as they get bored, they stop being productive and they basically stop working and they check out and go home. And that's something that everybody has to be aware of and try and avoid if you can, but sometimes it just does take hard work to get things done. Persistence is a key quality. And when I see engineers just saying, I'm bored on my particular project, there's some part of me that I don't like about it. But also there's like the opposite, and this is not an engineering problem generally, this is a business problem, and it's the idea of the sunk cost fallacy, where you've put so much effort into a product that you really don't want to throw it away. But you have to throw it away, because no matter what you do from now on, it's not effective. You're not improving the product in any way. So, and this is the problem with the Vegatis. Oops, sorry about that. Bit of AV issue. But the problem is that I was wishing I could start to formulate some real metrics here. And how do you measure when is the best time to stop? And I don't know what they are, because it's really vague. When I've been on projects that are starting to sort of slow down and become a little bit stale, there's like lots of different metrics. There's like enjoyment factor. Is it enjoyable anymore? There's how much interest are you getting from the business? Do they care about what you're doing? There's other people. Are people getting bored in their job? Communication. How much communication is going on between the team? Are they talking to each other anymore? Are they discussing problems and future ideas? And Yeah, I wish I could. That's not the best I can do. Persist until you have that sinking feeling. I think it's quite intuitive at the moment in time, but maybe with a bit more work, I can maybe formalize that a little bit. But you have this sinking feeling that the project is stalling. Yeah, stalling is a good word. You're kind of gliding along and you're starting to stall. And maybe that is the perfect time to break. Okay, I think that's about it for me. So thank you very much. Check out the website and talk to me more if you have any interesting philosophical ideas about engineering and research. Thanks a lot.
All right, so I think we have time for a couple questions, so please stick around if you would like to hear the answer.
I spoke too fast, sorry.
That's good. A lot of sessions don't have time for that, so it's good to have time for some questions here. So one I have here, it says, so scientific hypothesis involves testing the null hypotheses and rejecting them, rather than just supporting the hypothesis that you have. How does that fit into?
No, that's perfectly right. So the idea is that if you're trying to prove your own hypothesis, you're biased to trying to prove that hypothesis. And obviously, if you're set out to find a new JavaScript framework to your front-end developers, you could probably find some quite artificial reasons of why it's better. You might say it's prettier, or produce better UIs or something. So yeah, the way that they tackle that is they try and evaluate the null hypothesis, which is like the opposite of that. They basically try and come up with ways to disprove your theory, but then make sure that that is not correct. So it's a bit of a double negative if you understand that. So yeah, it's the idea of trying to prove your theory by proving that all of the alternative theories are wrong. And that's the scientific and best way of doing it. But unfortunately, that would require you to evaluate every single JavaScript framework. And given the time restraints that you have, that might not be feasible. So yeah, there's definitely a trade-off that you have to do.
Okay, then I have another question here. What is one thing to take away from this session? Should I do research, improve my skill, or apply them and repeat?
Whoa, one thing. I think the one thing that you should take away is the idea of continuous improvement. All of the greats were prolific readers. It might not come as a surprise. They were prolific readers and experts in not in only one field. They were experts in many fields, and they did that by continuously improving themselves. So irrespective of whether you think you're a researcher or an engineer, just the idea of continuously reading and improving all of these soft qualities that are maybe not related to technology at all will make you better people and better engineers.
I have one more question in here. Who drew the fantastic pictures you have on your slide?
I did, as you can probably tell. Did you like them? Yeah, probably not.
So that's all the questions I have for now. There's still a bit of time left over, so if you have any more questions, you can also just raise your hand, we can get to them, or you can just come up to the stage and talk to Phil. I'm sure he'll be happy to answer any questions you might have. Other than that, feel free to head out and enjoy the next break. See you back in here for the next session, hopefully. Thank you.
Thank you.